All right, everyone, you can check your attendance using your clicker. It's in the background. Just click it anytime you want. No, it's a snowy day, so some of you are probably come late.
I've been moving because I had to switch apartments today. I don't have
That's fine. I'll give you, great later. Okay, and so the homework 2 will be assigned later today. And I assume everyone already submitted your homework 1. If not, today is the last day to submit your homework 1. It's already a week past due. So if you haven't submitted, make sure you do it today, because tomorrow I'm going to post the solutions. And I wouldn't accept any homework 1 after today. Okay, so we're going to continue where we left in the last lecture, I think, which is last Wednesday. So we talk about the system of non-interacting particles. We can, the basic idea is if you have a Hamiltonian that is given by a quadratic Hamiltonian in the creation and annihilation operators with some coefficient Tij. Sorry, I should write this in the front, but it's the same thing. And then you can also have some diagonal terms like this. So this is a very typical Hamiltonian in the second quantization form for non-interacting particles. And here it's discrete, so we actually put the particles on a lattice. We can also do it in a continuous way, just to imagine that you change these sum to integrals. But the discrete ones are easier to deal with because you can actually diagonalize these coupling coefficients to make it non-interacting. So the idea is you first define some matrix H here, which is basically made of these coefficients. Tij is on the off diagonal and mu I is on the diagonal. So you make a matrix and then you diagonalize this matrix H here. And this is going to give you basically the eigenvalues, which I call the epsilon k. And this will actually transform the Hamiltonian into basically these non-interacting particles. So if you come late, make sure you use your clicker to check attendance. It's in the background. Just click any button there. Okay, so and in the last lecture, we talked about a very specific case where these coefficients are given by the time binding model. In this case, you can actually find the epsilon k's analytically for that very particular case of typically I will put Hermitian conjugate here plus the Hermitian conjugate, and then you have some mu sum over I, AI dagger AI. So in this case, we can actually find this epsilon k. This is a single particle energy spectrum. Analytically, it becomes this 2 times cosine of 2 pi k over n, and there's a t here, times t, then plus mu. So that's the expression. And then we talk about some detailed examples of how this is going to affect your ground state. The ground state basically are the state where all the negative energies are filled with 1 fermion and 0 when the energy is the epsilon k is positive. And for bosons, it's actually a lot simpler. So if the minimum of epsilon k is actually negative, then all the bosons are going to go to the minimum energy mode. So that is the case for bosons. I'm just going to rewrite it here. So for bosons, so if the minimum of epsilon k is smaller or equal than 0, then the ground state, let's just say smaller than 0, because equal to 0 you have degeneracy, so you can have degenerated ground state. The ground state will be all particles in state k minimum. So here k minimum basically is a k that minimizes epsilon k. Right. So remember this cosine has a bottom there. So that's basically the case for bosons. So we're going to keep talking about bosons for this lecture, and especially we're going to introduce some interactions, because so far this is all for non-interacting particles, either bosons or fermions. But in practice, of course, this is only an approximation. All particles interact to some extent, whether weak or strong. And today we're going to talk about weakly interacting bosons, and that is very important because this is kind of like the fundamental model for a Bose-Einstein condensate. And talking a little bit more about Bose-Einstein condensate, you can already get the basic idea from these non-interacting bosons, because you basically get all the bosons, into the same state K. Here, K just minimizes the energy spectrum, and typically this point where it's minimized is the point where the actual atoms have zero kinetic energy. So that basically means that all the atoms are basically stationary. They're in the lowest momentum state. And that is called the Bose-Einstein condensate, and this is actually be awarded the Nobel Prize in 2001 by 3 physicists that first realized it in the lab. And I actually want to show you a brief video talking about how a BEC is created in the lab. If you are in my undergraduate quantum mechanics, you've probably already seen this video before, but for some of you, this is the first time you're going to see this. No sound. Let's see. This is muted. Okay, good.
Bothered with hundreds or even thousands of a degree for that matter, aka a millikelvin.
We are bored by millikelvin. We like to go to nanokelvin. That is
nanokelvin?
Nanokelvin. That would be a billionth of a degree.
A billionth?
Absolute zero. It's very cold. It's a million times colder than interstellar space.
It's just about the lowest temperature ever reached. A place so clear and cold, physicists can see the fundamental laws of nature in action. MIT's Martin Zwierlein is going to use sodium atoms to show me how to get there, the final frontier of cold.
Wow. And so how do you do that?
So we can start over there at the oven.
The oven.
Step 1, cook up some sodium atoms, same kind in your table salt, to about 700 degrees Fahrenheit. That way you can separate them.
You want to get single atoms to play with, single sodium atoms, lots of them, a whole stream of them.
Step 2, hit them with lasers.
I know you MIT guys have the reputation of being very smart, but I have a little tip for you. Lasers are hot. You might be a little backwards there.
Yeah, you might think about Star Trek where they kill people with lasers. Turns out here, we cool atoms down with lasers, and they get a recoil from it. Just if you hit a billiard ball with another billiard ball.
In other words, when you hit atoms with just the right amount of laser light, it acts like a little shove in the opposite direction that the atom is moving, slowing it down.
If you look down here, you will actually see the cold clouds right there in the center of the vacuum chamber.
So that glowing star thing?
It looks like the sun.
It ought to be super, super hot.
No, it's actually extremely cold. Those are a billion atoms cooled to a millikelvin.
1,000th of a degree above absolute zero. But lasers can get us only so far.
You cannot reach the nanokelvin temperatures just with laser cooling. So we need another technique.
Which brings us to step 3. Get out your coffee cup.
What takes over after laser cooling is what we call evaporative cooling. It's the same thing that happens to your coffee right now, because it's just cooling down. So if you now force it a little bit by blowing on the coffee, you speed that process up. The coffee gets colder more quickly. That's exactly what we do here.
But instead of a coffee cup, Zwierlein uses a cup made of magnetic fields to trap his atoms. Then he blows on it with radiation and lowers the rim of the cup to let the hotter atoms escape.
So now we're going to do this coffee cup cooling. It's going to bring us to nanokelvin. Okay, ready for this?
Yes.
Let's do this. So, can you please switch on this stuff? Do this. This is great. Let's switch on this guy. And then this awesome knob here.
Press the awesome white button.
Fantastic. So that's good. Please press F12.
Always wondered what F12 does.
You see now the atoms are cooling because the cloud size gets smaller and smaller and smaller. Here you see the temperature drop, 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 drop.
Oh, wow.
It takes a few minutes, but eventually the atoms become so cold, they lose their individual identities altogether and coalesce into that new state of matter called a Bose-Einstein condensate.
Wait a minute. Okay, so
Yes.
that's the condensate?
That's the condensate.
But look at the temperature.
Yeah, it's very cold.
177 billion.
Billionth of a degree.
177 billionths of a degree Kelvin.
I just want to add something quick. You see that cloud? It actually loses all the sort of position information. All the atoms are in the momentum eigenstate because that's the epsilon k you are minimizing. Remember in the last lecture, we talked about that, this k actually stands for the lattice momentum. So you see, initially you can actually see a lattice of atoms. By the end, they're just in the momentum eigenstate. So the position is completely uncertain. So that's why you see that sort of cloud of atoms there.
This is the coldest spot in the universe right now.
It's
Right here.
amazing. So not even in outer space.
No. Outer space is a million times hotter.
Not the dark side of the moon,
No, it's like all hot.
comets,
Terrible, yeah.
black holes, nothing. This is it. In this room.
Yes.
That's amazing. I would ask its autograph.
Yeah.
But it's not about setting obscure records. What Sphereline is excited about is what these exotic states of matter can teach us about the universe.
Our puff of gas teaches us about the neutron stars. Or, split second after the Big Bang, there was this weird form of matter called quark-gluon plasma.
A super hot type of matter in the early universe that would give rise to everything we see today. So you're telling me that this tiny, freezing cold dot can teach us something about enormous, blazing hot stuff?
That's the fun part of physics. It connects these very different areas. The very hot, very cold, everything is governed by the same laws.
Amazingly, what happens at these ultra-cold temperatures is that atoms get so smeared out, their waves start looking indistinguishable from those of super hot particles under extreme pressure. Like those inside the inner core of neutron stars. So dense, a teaspoon of them weighs 10 billion tons. Sphereline and others can now simulate substances like this in their labs and probe their mysteries. That's incredible! And then in a couple more years, you'll finally do it. You'll hit 0.0, absolute zero, and we'll be done.
Yeah, unfortunately, it's never possible to reach absolute zero.
What?
There's always going to be a little drop of energy sitting around somewhere.
Turns out, it's impossible to get to absolute zero because no matter how cold you get, everything has tiny quantum jitters. And where you have motion, even a tiny amount, you have heat. But that's not stopping scientists from getting even colder to explore the fundamental laws of nature and how our universe came to be.
Just the way noise can drown out music, heat is like the noise that obscures things. If you get things really cold, you sort of drown out, you damp down all the noise, and you can listen to what nature is whispering to you.
I'm about
All right, so the guy that appears at the end is actually Eric Cornell. So he's in CU Boulder, and he actually got the Nobel Prize just because this discovery of BEC. And the main speaker, Martin Zwislein, so he's a professor at MIT, and he's actually a student of Wolfgang Kennedy, who also co-invented BEC and got the Nobel Prize. And when I was a PhD, I actually was in the same big team with Martin. I was a student. He's already a young professor at MIT, and he's really smart. And he actually leads this effort in trying to do quantum simulation, with fermionic atoms to basically simulate high-temperature superconductors. It's a very challenging project, but at least he made some very nice progress on that. And BEC is kind of like now something you have to first create in order to do any quantum simulation with cold atoms, because BEC is basically the ground state of weakly interacting bosonic atoms. So you have to first basically cool these atoms to ground state so they're not moving around, and then you can, for example, turn on some interactions or some chemical potentials, and then you can try to see some interesting quantum phases. So usually the first step you do is to create a BEC. And as shown in this video, the typical steps is first you do laser cooling of these atoms. They have to be bosonic, right? So they have to have integer spins for this to work. And then after it's cooled to millikelvin, then you do evaporative cooling, which is kind of like you put them in a potential like a coffee cup, and then you lower down the potential edge. Question?
What would give make an atom a boson? Because aren't they constructed out of fermions? Like, what would give an integer spin?
Yeah, it's the total spin of the whole atom. So you need to count the nucleus, right? So how many nucleus spins you have and how many electrons you have, and if the total spin is an integer, then it's a bosonic atom. And typically that depends on the isotope of the atomic species. So for example, the popular ones are like sodium, rubidium. So these are the commonly used atoms to create BEC. And usually they are alkaline atoms, basically the first column in the periodic table, and you want to choose the isotope such that they actually have integer total spin. But you can also find isotopes which have half integer, and they will be fermions.
It
Yeah.
also depends on whether it's ionized or not, right? Or are we just specifically talking about neutral atoms right now?
Yeah, we're talking about neutral atoms. Yeah, we're not talking about charged particles, which are ions. For the ions, you can't actually. Well, it's possible to create a. It's not possible to create a BEC for ions because they're charged and you have Coulomb repulsion between them. So usually people just do it with neutral atoms. And after the evaporated cooling, usually you will get already very cold, like in this nano Kelvin region, at least in micro Kelvin, and they are so close to the ground state because the temperature is very low right there. They're so close to the ground state that they're basically not moving, or the speed is very slow, so they basically get trapped. And then you can do all kinds of things. You can even use it for quantum computing. If you load it into a lattice, then each atom can be used as a qubit. Yeah. All right. Any other questions? Okay, so that's kind of the just to motivate you of why we're interested in bosonic atoms and the BEC. And now we have to introduce some sort of mathematical tactics to deal with them, because in practice these atoms will of course interact with each other. So you can't just use this sort of non-interacting Hamiltonian we are dealing with before. So this is a simplification. So what we think about how to introduce interactions, on a physical basis, and how we deal with the interactions. And at the end of the day, I can tell you that we still get something close to this. We will still get basically all the particles in some lowest energy eigenstate, but it's not going to be simply just this momentum state K here. So it will be something slightly different. And that is kind of always the idea. If the interactions are not very strong, then typically you will do some tricks. At the end of the day, it reduces to some kind of different non-interacting particles. It's not the same, but it's a little bit different from before, and the same picture still applies. We're focusing on bosons here. I don't have time to talk about interacting fermions, but the idea is very similar. So if you, like in a lot of materials, the fermions, the electrons, they are also going to be interacting, but the interactions are not very strong, at least in some situations. Then in this case, you can also approximate these non-interacting models by weakly interacting a model called the Fermi liquid. At the end of the day, you will get something close to what we talked about in the last lecture, but slightly different. Okay, so now let's focus on weakly interacting bosons. And I'll talk about what weakly actually means just in a second, because we need to make some approximations to assume that the interaction is weak enough. Okay, so here, also try to sort of mimic what's happening in that experiment I just showed you in the video. We're not going to actually, put the atoms in the lattice. You can do this on a lattice, but it doesn't really matter too much. Usually, when you're doing laser cooling and also the evaporative cooling, these atoms are just kind of in a gas, so they're all bunched together. So we're actually in a continuum, so the space is continuous. And in this case, we can basically find the Hamiltonian for these atoms. So the Hamiltonian will consist two parts. One is the kinetic energy part. The other one is the interaction energy. So we're going to write them separately. So the kinetic energy part, and we're going to directly use the momentum basis because this is this is kind of like the eigenbasis for non-interacting particles. So the kinetic energy, we're just going to write it in T. Again, this is the second quantization picture. So we just have P squared over 2m and Cp dagger Cp dp. And so this is kind of very similar to this part. This epsilon k here, it takes the cosine, but if you expand it near the bottom of it, it actually looks quadratic in terms of the momentum. So here, because we're not putting any lattice, it's just going to be simply p squared over 2m, and that is the kinetic energy of a particle with momentum p. And these Cp dagger Cp just count the number of particles with momentum p. So this makes intuitive sense. And integrate over all the momentum, you get the total kinetic energy. And then what is kind of more complicated is the interaction or potential energy. We're not going to add any real potential energy here because at the end of the cooling, we're going to remove all the potentials, right? We use for evaporative cooling or laser cooling. So at the end of the day, you just have basically a bunch of atoms sitting there. So the only potential energy is the interaction energy. Question?
Is this all dimensionless?
We can assume it's in 1D for simplicity. Yeah, but it doesn't really make much difference to go to higher dimension in this case.
Or unitless?
Oh yeah, unit. It does have the unit, right? Because when you do this integration, it does give you the unit of energy, right? Because it's p squared over 2m, right? So the unit is correct, right? If you are in a high dimension, then it's not just dp. It's like dpx, dpy, dpz. But the idea is very similar. Okay, so now let's talk about interaction energy. And the basic interaction energy here is that if you have, even if these are bosonic atoms, they can actually be at the same position. But you will imagine that there's going to be a little bit of repulsion, because what's going on, if these atoms are actually exactly on top of each other, then these atoms, they are also made of nucleus and electrons. The electrons are actually, charged, right? If you have two atoms wave function which are exactly overlapping with each other, that means the electrons are also having overlapping wave functions. And the electrons don't like each other because they actually have, Coulomb interactions, right? Because they're repulsive. If you put two charged electrons, they're actually going to repulse each other. So that means in general, if you just stack two bosonic atoms on top of each other, there's going to be a large repulsion energy. So this is the physical source of the interaction. Question, Bora?
What is the repulsion energy at like nanokelvin essentially like become negligible?
I don't think it's negligible even at nanokelvin. It's different, right? So when we are talking about the temperature, it's actually the average kinetic energy. And the interaction energy does not affect the temperature. So it's different. So the temperature is only associated with kinetic energy. So think about like classically, temperature is basically how fast these individual particles actually move, right? For example, if you have a hot cup of coffee, what that actually means is the molecules there are actually moving very fast. They're doing Brownian motion, right? So when you are cooling this, you're only cooling down the kinetic energy part, and the interaction energy is still going to maintain, right? So that part is not going to go away. It's going to try to minimize the interaction energy by choosing the proper distance between the particles. But yeah, you're not going to kill the interaction energy. All right, so based on this, you basically just get a density interaction. If the two atoms are at the same position, then you're going to get a repulsion. And we talked about this type of interaction before. It's called the on-site interaction. And this interaction energy, we can write it in the following way. So we have a coefficient u here, and then we have ax dagger, ax dagger, ax, ax, dx. So this is something we actually talk about when we talk about how to write the two-body operators, basically the interaction energy in the second quantization form. You'll get these four operators, two creation and two annihilation operators in this particular order. And if you swap the order, you actually can find that this reduces to nx times nx minus 1. And this is the reason that you only get interactions when you have at least two particles at that position x, right? You have either 1 or 0, this product goes to 0, which makes sense, right? Because you can only have interactions when you have two particles at the same position. And here we're only going to keep the on-site interaction. So basically, when the two atoms are exactly at the same position x, we're going to assume that there's interaction energy basically given by u here. Right? If you have more than two, then it's going to scale as nx times nx minus 1. But if the two atoms are actually at slightly different position, we're going to just ignore the interactions between them. This is, of course, not exactly true, but it's a good level of approximation from the non-interacting case where there's no interaction. Right? So this is like the first order approximation to the true interactions between the particles. In practice, if the atoms are well separated, you can ignore the interactions, but once they get closer and closer, interactions get stronger and stronger. And typically it goes exponentially stronger when they get close. So this is a good level of approximation, just to assume that we only care about interactions when two atoms are at the same position. And the total Hamiltonian, of course, is just going to give, it's just going to be a sum of these two parts, the kinetic and the potential energy. And the goal here is to find the ground state as well as the basically the energy spectrum and the eigenstate of this Hamiltonian, right? So suppose you cool this system to 0 temperature, then you should be able to get to the ground state of this combined Hamiltonian. This is certainly not something we saw before, because if you just have that kinetic energy, that's very simple, right? Because if you look at that T here, the ground state should just be all the atoms into the p equals to 0 state, because p squared over 2m is minimized by p equals to 0. So without the interactions, this is trivial, but with the interactions, we don't know actually how to do it yet. Okay, so how are we going to do this? The first thing you notice is that these, I actually use A instead of C because the interaction energy is actually written using creation operators in the position basis, right? Because that's kind of the basis where it becomes diagonal, and the kinetic energy is written in the basis in the momentum basis because that's where the kinetic energy is most conveniently written. So apparently, in order to try to solve this, we have to basically change them to the same basis. And in this case, we're going to actually change the interaction energy to the momentum basis as well. And this is something we actually did, a couple of lectures back. So we're going to do this Fourier transformation to convert the AX to the CP. So this is a basic transformation. It's a unitary transformation. So here we can write AX as 1 over square root of L, and then e to the I px over h bar, Cp, dp. This is very similar to this discrete Fourier transformation we did in the last lecture for that time-binding model. But here we're doing it in the continuum, so we change all the summations to integral, and the prefactor 1 over square root of L, that's kind of similar to the 1 over square root of n we did in the discrete case. And then we're going to do this integration here. So that's just the standard Fourier transformation to go from the momentum space to the position space. So once we do that, we can basically rewrite this interaction energy V here using the momentum basis. So this is going to look a little bit ugly because we have 4x here. And each time when you're doing this integration, you're going to introduce a new p, right? Because this p is kind of like a dummy variable in the integration. And once you have 4ax, you are going to have 4 p's. So this is going to have basically a u over L squared. And then we're going to have 4 integrals here. So I can call it dp1, dp2, dp3, dp4. And again, the reason why we have 4 p's is because each of the ax on the top, we're going to introduce the integration on some p. And that p is a dummy variable. So we're just going to call it p1, p2, p3, p4. And we're also going to have a dx here. So I'm going to keep this dx here. And then the integrand is going to look like this. So we have e to the I x, and then we're going to have p1 plus p2 minus p3 minus p4. And the p1, p2 are for, in this case, are, let's see, so now maybe I should put a minus sign here. This doesn't matter, it's kind of a convention, just make sure I'm doing things consistently. So these two ax, they're going to have negative p's, so that's why I put p3 and p4 here, and there's also an x there in the front. And then the p1, p2 are for the ax dagger, so those ones I have the positive sign. So that's basically the exponent. And then I'm going to have these CPs. So I'm going to have CP1 dagger, CP2 dagger, CP3, and CP4. So this is the whole expression. So there's actually 5 integrals of 1 over dx, and there's 4 integrals over momentum. And then there's this Fourier factor e to the I there. Okay, so that looks a bit complicated. We're going to gradually simplify this down to something we can actually manage. So the first thing we notice is that we should have momentum conservation here. And there are a couple of ways to see this. So first, if you look at this, this Fourier factor here, and we know there's this delta function. So if you have 1 over L and then you have e to the I, let's call it p. Let's call it px dx, and this is actually equal to delta of p0. So if you do an integration like this, then unless p is equal to 0, this integration is going to give you 0, and that's kind of similar to your homework 1 problem. So that's basically the mathematical property of this Fourier integral. And according to this, then going back to this, this basically means since we're doing an integration on all the p's, effectively we actually require p1 plus p2 minus p3 minus p4 to be equal to 0. So you actually require this. You can call this whole thing p if you want. So that has to be 0 because we are doing an integration on this and over dx here, right? So you can treat this whole exponent p1 plus p2 minus p3 minus p4 as just some p. And according to that mathematical identity here, you will require this to be 0. So that's what makes sense mathematically. Physically, this also makes sense because this is basically the momentum conservation, right? So this interaction energy here is going to conserve the momentum in the sense that you can create, remove two particles and create two particles, but the total momentum cannot actually change. So we also talked about this before. So using this property, we can at least remove the integral over dx. So that's going to give us a delta function. And because these p's are not independent, we can also, so let me first do this step. So we'll get u over L here. So there's a L squared because of this integration here. But then this is going to remove one L. So now I only have a L there instead of L squared in the denominator. So then I still have these 4 integrals over P. Then I will have a delta function here. So P1 plus P2 has to be equal to P3 plus P4. And then I have dP1, dP2, dP3, dP4. So what I removed is the part with integral over x, right? So I basically removed this part. So this part actually just becomes this, using this.
CP instead of DP.
Oh, sorry, I removed the CP, sorry. So CP should still be there. Okay, let me correct this. Thanks for pointing that out. So this is not the DP, but the CP. That part doesn't change. Okay, yeah. So basically the highlighted part, I just change it to the delta function. So there's no integration over x anymore. So then the last step is to also, using this delta function property, we can at least remove one integration over p. So it becomes just 3 of them in this case, right? Because we basically just require, for example, p1 to be equal to p3 plus p4 minus p2. But this part is, we don't need to simplify it at this point. We can just keep this, but just keep in mind that this can be further simplified to just 3 integrals. I'm going to write it anyway. So we can just integrate over 3 of them, and the P4 we can actually fix it. So we can just do this, and then the P4 we can just change it to P1 plus P2 minus P3. So we can do that. So it's effectively just 3 integrals in this case. Okay, but either it's either 4 integrals or 3 integrals. This is still not something we can treat because you can see these operators are going to be quadratic. So you have 4 of the operators in total. And remember, if you want to deal with a non-interacting particle system, then you have to deal with something like a quadratic Hamiltonian, right? So if it's quadratic, this is not something we can solve analytically, and it's actually, having interactions. It's not interacting. Okay, so now it's time to make approximations. I said that we have to make approximations in order to treat this. So the approximations here is going to be assuming that the interactions are weak. So we're going to assume that the U here, so the U represent the interaction, is going to be weak. So it's kind of close to 0. It's not exactly 0, so it's close to 0. And so let's first think about what's actually going to happen in this limit. So if the interaction is weak, so first, without interactions, we know the ground state is just going to be all the atoms in the 0 momentum state. So we can call, so the number of atoms in P equals to 0, so that's a 0 momentum state. We can call that N0, right? So the subscript actually stands for P equals to 0. So the number of momentums in P equals to 0, we call it N0. In the non-interacting case, this N0 is just going to be equal to the number of particles you have in your system. So N0 is just equal to N. So number of total particles, or total bosonic particles. So that's that's actually U equals to 0. So now if U is close to 0, then what we are going to assume is that this N0 here, it's not going to be exactly N, but it's going to be at least much larger than 1. So that's the first approximation we're going to assume, right? Because first we are talking about BEC here, so we're going to have a lot of atoms, right, loaded here. So apparently the total number of N should be much larger than 1. So usually you have like at least 1 million atoms when you're talking about a BEC. So with some interactions, we're still going to assume most of the atoms are going to be in the 0 momentum state. So it's going to be some huge number. Okay, at the end of the day, we're going to reveal that there are also some atoms in some state with finite momentum. So the distribution is not exactly a delta function. So even if you measure this in an actual BEC, you're going to find that the momentum distribution, the number of particles with different momentum kind of falls like a Gaussian. So it's not exactly, all at the zero momentum. So you'll never get a delta function, but it's kind of close. Okay, so with this approximation, so there are a couple, mathematical equations we can write. So the first thing is if you look at the annihilation operator for p equals to 0, so this is actually, Cp with p equals to 0. So Cp is the annihilation operator for momentum p, right? So we remove a particle with momentum p. So if you look at C0, then it acts on the ground state. So this is the, I can just call this precise ground state. So this is the actual ground state of the weakly interacting bosons. So it's not the ground state for non-interacting ones, just to be clear. This is a ground state we're trying to solve. Right, so this is a ground state for weakly interacting bosons, and we just know that this should actually have at least a lot of particles with zero momentum. And in this case, we can actually approximate this by just square root of n0 times precise ground state itself. So that's the approximation we're going to make. So what is the approximation here? So usually when we have C0 acting on the ground state, so we have C0 acting on some state. Let's say you have n0 particles, right? You have a Fock state here, and then typically it just goes to square root of n0, and then we have n0 minus 1, right? So this is a standard rule for applying annihilation operator on a Fock state, on an eigenstate of the number operator. So it goes to a square root of n and then n0 minus 1. But since here we assume n0 is much larger than 1, so suppose n0 is like 10,000, and then this is like 10,000, this is like 10,000 minus 1. And these two states are barely different, right? You just remove one particle from a state with many particles. So this is where the approximation actually holds, right? So we're going to assume that they don't actually change the state much. You're just going to get a coefficient of square root of n0. So that's the approximation we make. So later on, we're going to reveal that there's actually going to be a state that exactly makes this true, and that is actually close to the real ground state of these weakly interacting bosons. But we're going to talk about that just in a second. So that state is called a coherent state. The discovery of that actually leads to a Nobel Prize, in another year. So question, Richard?
With u being approximately 0 or u being 0, which one is inferring that there is weak interaction?
So u being approximately 0, that's weakly interaction. So this is no interaction, right? So this is weak interaction. Yeah, just to be clear. Okay, so this is going to be true, and at the same time, the C0 dagger, we just take the Hermitian conjugate of this equation, so we can also approximate that by square root of n0 times the ground state itself. And this again is approximation because usually C0 acting on a Fock state is going to be C0 dagger. Acting on a Fock state is going to give you a square root of n0 times, I think it's n0 plus 1 times n plus 1. Right, so that's a usual rule, n0 plus 1. But here, because n0 and n0 plus 1, they're very different, we're going to just assume that these can be replaced by n0. So it's kind of a weird approximation. But what's going on here is you are going to find that when you apply this annihilation operator for the zero momentum on your ground state, you're just going to get a number times that state. So that's kind of the idea. You're just going to get a number times that state. And in this case, we can actually just replace these operators C0 and C0 dagger by a number. So this is just roughly equal to square root of n0. So that is the approximation we're going to make. And this approximation has a famous name. It's called the Bogoliubov approximation. So Bogoliubov approximation. So this is named after, I think, a Russian physicist named Bogoliubov, who basically first used this to treat interacting bosons. And I briefly mentioned this just a while ago. These approximations can be made exact. If the ground state is a coherent state of atoms at zero momentum. Okay, so what is a coherent state? So this is a pretty important concept in quantum optics, but it's also relevant here. So I'm just going to talk a little bit about it. So a coherent state, so it's basically a state defined in this way. So typically it's denoted by a ket of alpha, where alpha is basically a parameter of the coherent state. And this coherent state is given by a kind of a weird a superposition state of your Fock state. So n from 0 to infinity. So we have alpha n over square root of n factorial times n. So I'll explain why it has this kind of weird superposition. So first, the coherent state is nothing but just a superposition of your typical Fock state, the number state, right? So you basically have a superposition of having 0 particles at 0 momentum, 1 particles at 0 momentum, 2 particles at 0 momentum, and so on. So you basically have a superposition of different states with different particles in it, right? So that's the idea. But then you have this kind of complicated superposition coefficient there. So that's what the coherent state is. And the reason why this state is special and is called coherent is just because this is actually an eigenstate of the ionization operator. So we can apply the ionization operator C on alpha here. So here I'm just going to take that to C0. It's the same thing. We're only talking about the 0 momentum mode here. So we're just going to pretend that there's only one type of particle in your system. So if you apply this operator on this state alpha, actually some magic happens. It's actually not too hard to see, but if you apply this C here, so each time you're going to get like a square root of n times n minus 1, like what I said on the top here. But then because there's an infinite sum here, at the end of the day, what you're going to show is that this is just going to be equal to alpha times alpha. I'm not going to waste time showing the math. If you're interested, you can do this yourself. It shouldn't be very hard by using the standard rule of C acting on n equals to square root of n times n minus 1. It's a very interesting mathematical relation. You actually find that this is the eigenstate with the eigenvalue exactly given by alpha. And because this annihilation operator is not Hermitian, so this alpha in general is actually complex. Only for Hermitian operators, we are guaranteed to have real eigenvalues. So in this case, they're actually complex. So this is first invented by Rob Glauber from Harvard University, and he actually got the Nobel Prize for this. And he basically, was studying the state of, it's basically the state of light in lasers. So it turns out that the photons in the lasers actually are very close to be in a coherent state. So this is also the state for lasers. So for some, sometimes people actually call lasers are actually a Bose-Einstein condensate for photons. It's kind of because of this relation. We're going to show that for these weakly interacting bosons, the ground state is going to be a coherent state. And then for the laser, you can actually think about it as a Bose-Einstein condensate for the photons. Photons are not really, atoms with mass, but you can think about it as just all the photons are in the same state. So that's kind of what the spirit of Bose-Einstein condensate. And this is also the reason why the laser is perfectly monochromatic, because all the photons are actually in the same state. So it's actually in that coherent state. This state has very nice properties. I don't have time to talk about it. So for example, these alpha states actually also make a basis of a Hilbert space, but the basis is over complete. So there are some fun things about this. And there probably will be a homework problem related to the coherent state, just to let you play around with it a little bit more. Question? Yeah.
So in the laser where you have the coherent state,
yeah.
I guess I think of the coherent state as being this case that is not zero interaction, so there are weak interactions.
Yeah, that's a good, we don't actually get it here because Yeah, the lasers are different because first they're made of photons, and here we're talking about particles with mass. So at the end of the day, you are going to get slightly different behavior. But for lasers, photons typically don't interact. And the reason why you can create a state of this is also not because it's a ground state of some interacting model. It's just the medium that generates laser. So you need to use some kind of medium that does population inversion. It's usually some sort of nonlinear crystal. And that actually generates a photonic state that looks like this. So the laser itself is not a ground state of some interacting Hamiltonian, right? You can't cool, the photons in that sense, right? So it's different. You just get that state. And here we're really talking about we have interacting atoms. We try to cool to the ground state, and that's the state we get. Interestingly, there is a very nice connection between the two. You can really think about laser as a both instant condensate for photons. Okay, and the reason I mentioned about the coherent state is this state actually make this Bogdanov approximation actually exact. So if you apply on this, it's just an eigenstate. And we all know that in quantum mechanics, if the operator is applying on the eigenstate, you can just replace it by a number, right? So that's basically the number here. And because this number is real, the C0 dagger is going to be equal to C0. I said that the alpha in general can be complex, but it can also be real. In that case, it's going to be the same thing. Okay, so all right. So let's now look at with this approximation whether we can make this this complicated expression here more manageable. Okay. So the first thing is that the dominant term in this expression. So let's just look at this expression here. So you can also look at the bottom one, but it's kind of similar. We just keep in mind that the P1 plus P2 is equal to P3 plus P4. So the dominant term in this expression is going to be all the p's equals to 0. So let me just sort of rewrite this v here in the bottom, because so I'm still going to do the 4 integrals here. I think it makes sense a little bit more transparent. And I'm going to keep the delta symbol for now. So we have 4 of these creation or annihilation operators. And the general idea is most of the atoms are going to be in the state with p equals to 0. And if p is not equal to 0, then we would expect these CPs to be much smaller. So I'm talking about the size of the operator, which is not the exact language we should use. But the basic idea is that when you apply it on the ground state, then those operators will give you much smaller matrix element, because most of the atoms are in the ground state. And if you look at the typical matrix element for creation or annihilation operator, it kind of depends on how many particles you have in that state, right? It goes like a square root of the number of particles, because most of the particles are in the ground state. So that means this term is going to be dominated by in the zeroth order by just all the p's equals to 0. So this will give you the largest term here in the integration, right? This is integration. And the largest term is given by all the p's equals to 0, because this is just going to be the case where we have 4 of these C0s. And this is actually also equal to just N0 times N0 minus 1, as we talked about before. And here this N0 is just, we can also just replace it by the capital N, because that is the number of particles in with momentum 0. And especially with the Bogdanov approximation, we can really just replace these C's by numbers, right? And this N minus 1 is also not very important, so we can just call this N0 squared. Because N0 is a very large number. Okay, so this is a zeroth order approximation, and this approximation doesn't really give you anything interesting, because this just means the zeroth order approximation, or the largest term in this integration, is just going to be equal to this constant. So it's approximately equal to N0 squared. And we know if the Hamiltonian, you just add a constant to the Hamiltonian, it doesn't really change your eigenstates, right? It doesn't change the eigenstate, it doesn't change the dynamics of the system, because it's just a constant shift of your energy. It only creates some global phase in the evolution, and it doesn't change your eigenstate. It's just going to shift your energy by a constant. So that's not the interesting part. And as we usually deal with kind of like analysis of any kind of approximation or series expansion, we need to go to the next order. Okay, so what about the next order? So the next order is going to be it's kind of more interesting. You will need 2 of this to be 0. So 2 of P1, P2, P3, P4 are 0. The other 2 non-zero. Okay, so this is going to be the next order because you have to have this momentum conservation. So here we can actually have 2 different types of terms. So we can actually have, for example, P1 equals to, we can just choose whatever we want, right? So we can choose P1 and P3 equals to 0, and then because we have to have P1 plus P2 equal to P3 plus P4. Right, so this conservation has to hold. So we can choose P1 and P3 to be equal to 0, and then in this case P2 has to be equal to P4, right? We can choose, we can call this P. So in this case, this is just one of the case. So in this case, we can simplify this as basically we have 2 of the C0s, and each of the C0 will just reduces to square root of N0. So I'm just going to have an N0 here, and then we're going to have CP dagger CP. So this is one possibility, and certainly we can have other possibilities. Of course, we can just swap the row of P1 and P3, P2 and P3, P4. So that would be the same thing, but this term is not going to be very interesting. So it's going to be the same as before. So we can just swap this, and that's also going to give us the same term here. Okay, so there are more interesting things down below here. So we can also have, let's say, P3, P1 and P2. So these 2 to be 0. And in this case, we can have P3 equals to negative P4 equals to P. In this case, we are going to get terms like N0, and then we're going to have a C, P, and a C minus P. Yeah, so that's right. And then there's going to be a last case, which is P3 equals to P4 equals to 0. And then we have P1 equals to negative P2 equals to P. In this case, we'll get N0, and then we'll have CP dagger and C minus P dagger. Right. So I'm just writing this term in all these 4 different cases, because the next order requires only 2 of the P's to be equal to 0. Question, Bora?
So for these momentums,
Yeah.
I'm confused in how you could have 2 of them equal to 0 and then 2 of them be non-zero and still have momentum conserved, because I would think if 2 of them are non-zero, they would be equal and opposite.
Yeah, so that's exactly the case of 3 and 4, right? So if 2 of them are 0, the other one is going to be opposite, but you can also have 2 of them to be 0, and one of them is equal to the other, right? So these 2 are both, so there are basically these 4 cases. Right? So you can think, these are all the 4 cases you can think about, right? Because you want 2 of them to be 0, but you also want this momentum conservation. These 4 are the only possibility. Can you think about a 5th one? I don't think so. Right? It's just how you play around with this. Okay, so with all these 4 cases, we can basically simplify this this V here. So this is going to make a lot of simplification because we actually have 2 of them to be 0. So this integration actually changes to just a single one, right? Because there's only 1 P at the end after the reduction. There's only 1 P. So this whole integration just becomes a single integration over P. And this integration is going to assume P is not equal to 0, right? So we are going to assume the other 2 are non-zero. So this is going to be integration over P not equal to 0. And then we'll have CP dagger CP plus CP dagger CP plus CP dagger C minus P dagger plus CP C minus P. And then also plus that 0th order term, but this is not important, so we're just going to write a constant here. So this constant actually corresponds to the zeroth order, so that n0 squared here. So important part is the part in the integral. So this is the next order approximation when two of the p's are actually equal to 0. Of course, you can even go to the next order where four of the p's are non-zero, but that's kind of the next order, because the key is that the creation operators, annihilation operators with p equals to 0 are large, and the other ones when p is not equal to 0 is small. So we want to keep the leading order term. So this is the next order. So this is the minus sign here. Yep. Okay, question.
Where does the n0 term in the
Oh, did I?
second order? Does
Yeah,
it get
sorry. Yeah.
normalized out, or?
Yeah. Should be n0 here. Yep. There should be an n0 there. Okay. And thanks for pointing out this mistake. So this is important because we're going to define a new constant here. We're going to call n0 over L equals to rho. So the rho here stands for the density of atoms. So this is the density of atoms, right? Because we have n0 particle, in the momentum equals to 0 state, and that over the length of the system. We are assuming 1D here, so that's going to be the density. So we're just going to call this U rho here with this whole thing there. So this means we can now write the full Hamiltonian here. Everything is now written in the creation and annihilation operators in the momentum space. And this whole approximation we made basically simplifies this quadruple integral to just a single integral over P. And all these terms are actually quadratic. So the whole Hamiltonian is given by integration over P not equal to 0. And then we have the kinetic energy, which is P squared over 2m, plus the potential energy here. So this one, these two are the same, so there's a factor of 2. And then we have U times rho, because this prefactor is just equal to U times rho. And then we have Cp dagger Cp. And then we also have the second term here, U times rho. And then we have Cp dagger C minus P dagger plus Cp C minus P. And then we have an integration over dP plus a constant, which is not important. Right, so also notice that this integration is over P not equal to 0. For the kinetic energy, it doesn't really matter. If P is equal to 0, that term is 0. So we can totally exclude that term in the original integral. So this is a simplified Hamiltonian after this Bogdanov approximation. So we can see that now this Hamiltonian in the second quantization form actually is again quadratic in terms of the creation and annihilation operator. The only thing is we have these pair creation and pair annihilation terms. So these are the pair creation and annihilation terms. And the reason they are in this pair is exactly because of momentum conservation. So you can remove two particles, but they have to have exactly the opposite momentum. We can also create two particles. They have to have exactly the opposite momentum just because momentum has to be conserved in the system. Right? And usually you wouldn't have that if you don't have interactions. So these pairing terms are actually a result of the interaction. Whenever you see these pairing terms, it's usually because you have interaction in your system. And another very famous example are basically superconductors. You will get a Hamiltonian very similar to this. You will also have these pairing terms. Those are actually also due to interactions. So if you have no interactions, you can only get the first term, which are your standard non-interacting particle term. So the second term is purely due to interactions. Any questions? Yep.
Are there more combinations, like when you did the momentum P1 equals P3 equals 0? So if you get P1 equals P4 equals 0, wouldn't that be like an additional combination that would give you a factor of 2 in the potential calculation?
Sorry, which one?
For example, P1 equals P4 equals 0, and then P2 equals P3 equals P.
P1 equals to P4 equals to 0?
Yeah. So like that's an additional combination.
Let's see. So I think that's probably going to give you the same term. Can you?
Yes, but would that make like an additional factor because you would have to?
Yeah, let's try to write it down. I think I counted. So you are saying the P1 is equal to P4 equals to 0, right? Mm-hmm. And P2 equals to P3 equals to P. And is that actually the same as one of the terms here?
I think it'll should be the same as the first term,
You can either have.
but would that make like a factor of 2 in that term?
But if you write this down, what do you have? So let's try to write this operator down here. So you're going to get a N0 here, and then you are going to get CP dagger CP, right, in this way. And isn't that the same as, so this is going to be the same as these two. I think you're probably double counting. Let's check whether that's the case. Yeah. P2 equals to P4 equals. Yeah, I feel like that's probably a double counting issue.
Because P3 and P4 are distinguishable, right? So, like.
So you're basically saying I can have yeah, that's a good point. You know, yeah, I think we have to do this counting probably more carefully. I think at the end of the day, this is actually correct, but I don't have a good answer to you at the on top of my head. This is a good point. I'll check that. I think there's probably a double counting issue here. You can't actually count extra ones, otherwise there will be an extra factor of 2. Yeah, that's a good point. Yeah, your name is George, right? Yeah. Okay. Yeah, that's a good point. Yeah, I have to figure out whether there's an issue of double counting here. Yeah. Okay. Yeah. Question, Paul.
What's physically happening between those two different objects?
You mean which different?
Comparing 1 and 2 versus 3 and 4.
Those are fundamentally different. Yeah. So the thing George just said might be a double counting issue, but these two are fundamentally different from the first two. Because here you can actually see that I'm actually doing a pair creation and annihilation. So I'm actually creating 2 particles with opposite momentum and removing one. And the first two actually I don't do it. I just remove one particle at P and then create another particle with the same momentum P. Right? So physically they are different, right? It really just depends on which 2 particles you want them to be actually in the ground state, in the 0 momentum state. Right? So because there are 4 P here, then it really just, it's kind of like a combinatorial game, right? So which of the 2 you want to be in the 0 momentum, and the other 2 are basically the ones you want to create and remove. You can basically end up with these 4 different situations. Okay, yeah.
Could we spend some time talking intuitively about the terms in the Hamilton? Could you scroll down?
Yep.
Because I see the right side intuitively that makes sense because you're creating annihilating particles at opposite momentum.
Yeah.
So they're either, depending on the sign of mu, they're either attracting or repulsing each other with equal and opposite.
Yeah,
force.
yeah.
The first term I'm a little.
The first term is just MP, right? So the first term is actually easier to understand. So this is just number of particles with momentum P. For example, the P squared over 2m, that's just the kinetic energy, right? So you just count how many particles with that momentum. And this 2 U rho, this second part, is just a result of these ones, right? So some of the interactions actually just reduces to a potential energy. So you can really think about this U rho as, so this part is kind of more trivial because it just means with MP particles at momentum P, I'm just going to add an extra energy. And that extra energy is just equal to U times rho. And that's a constant. Rho is the density of the atoms, which is set to stone, once you load the atoms. And the U is the interaction energy, which is also a constant, right? So you're basically just adding a constant energy cost. And the other way to think about it, this is kind of like a chemical potential, right? So this is the cost for adding one particle to your system. Yeah, good question. So that's the first part. If it's just the first part, then it's kind of trivial, right? So we already know how to solve it. It's kind of very similar to what we did last lecture. So this is the energy spectrum, right? If you plot it, it's going to be like a parameter with a shift given by U rho, right? So if you just plot this, this is the energy epsilon versus P, then it's just going to look like this, right? So that's basically, this expression here. It's just going to look like this. It's shifted by 2 times U rho. And that won't be very interesting. The interesting part is the addition of the last part, the last term. Okay, so we're getting to probably the most math-heavy part of this whole course. So this next machinery is called Bogoliubov transformation. This is probably the most math-heavy part of the entire course. So before this part, we are mainly talking about some simple math with a lot of intuition and concepts. But now we're getting to a technique that really requires some math, but it's not super complicated. You can see it's pretty much all, high school math or maybe calculus a little bit. So this part is called Bogoliubov transformation. And the whole goal is trying to solve this Hamiltonian, right? So even though this Hamiltonian is a quadratic, we can't actually diagonalize it because of this last part, right? So the way to think about it is that this first part is already diagonal in the sense that it's just some number times NP. And if you use the many-body Fock basis with the creation operator as CP, that's already diagonal, right? But the problem is the second part. So this part is actually non-trivial because it contains this pair creation and annihilation term. And how do we deal with it? And Bogoliubov not only introduces this approximation, the key point of the approximation is to, at the end of the day, try to solve the energy spectrum of the whole system, right? And this is what the next part, Bogoliubov transformation, is aiming for. Okay, so this is also like a great idea for dealing with just a lot of many-body problem. So once you are getting something in this form, then you can introduce some new creation and annihilation operators to make this actually diagonal. So I can first tell you where we're going. So at the end of the day, we want to actually, So at the end of the day, we're going to change this Hamiltonian to something like some epsilon of p and then BP dagger BP. So I can tell you that's the final goal. We want to make it diagonal in this nice form. So we just have an energy spectrum and then we just have the number operator for something. And you can see I use a new letter B instead of C or A. A I reserve it for the position space. C is a creation annihilation operator for the momentum. And now I introduce something B, probably in memory of Bogoliubov. Everybody is using B. So what are these B's? So this is kind of the typical idea of a quasi-particle. So this is not going to be the original atom we are going to create or remove, right? So both the A and C's have physical meaning. The A's create a particle, create an atom exactly at position X. The C's create a particle with momentum P. But the B's is not a real atom. So it's a quasi-particle. And so we can first look at what's the definition of the B. So the BP is defined to be a cosh of theta. I know people don't like cosh. This is probably going to be something more complicated than you think. And then there's a sinh and the C minus P dagger. And then there's also the Hermitian conjugate, which is the creation operator for B. So that's the sinh of C minus P plus cosh of theta P, CP dagger. These two are just Hermitian conjugate of each other, right? So if you just take the Hermitian conjugate of the top one, you go to the bottom. The C minus P dagger becomes C minus P. So those are just Hermitian conjugate of each other. Again, this is for P not equal to 0, because for P equals to 0, it's kind of trivial. All right, so this is why it's a quasi-particle. So if you just look at this, for example, let's look at the BP dagger, the last equation here. So it's creating a quasi-particle at momentum P. And that quasi-particle, you can think about it, is kind of like you have some part which is just creating a particle with momentum P, but you also have some part that is removing a particle at momentum minus P. So it's really kind of like a weird hybrid thing. And one way to think about it, we kind of talked about this idea before. If you remove a particle at a momentum minus P for that first term, you can also think about it as creating a hole at momentum minus P. So this makes you understand this easier. So in some sense, this quasi-particle is a linear combination of the original particle at a momentum P and a hole at a momentum minus P. So you're actually creating a mixture of this, right? So each of the quasi-particle at momentum P is a mixture of a real particle at momentum P and a hole at a momentum minus P, right?
So that sort of accounts for degeneracy to some extent?
No, this is not really related to degeneracy because, we're not counting the energy spectrum here, and these coefficients are also not identical. So this is really just how you understand what this quasi-particle is. It's a combination of a real particle at momentum P and a hole at momentum minus P. So that's what the BP dagger is doing. And apparently doing this has a purpose. The purpose is to make sure that the Hamiltonian actually can be diagonalized into that red color equation, right? So that's the whole purpose. And there's also a free parameter here I didn't mention. That's a theta p. So theta p here. So this is a free parameter. It also has a name. It's called the Bogoliubov angle. And this is, we have to assume theta p is equal to theta minus p. And this is needed to make sure that these BP and BP daggers actually obey the canonical commutation. In your homework too, you're actually asked to show that the BP and BP dagger, this one actually commute, not commute, but actually the commutator is equal to 1. And if they're different, if you have like a BP and BP prime, or a BP and BP dagger prime, so this is actually going to be equal to 0 if P is not equal to P prime. So in the homework too, you'll be asked to show this. And the way you show this is because I already write the expressions. And at the end of the day, you have to use some identities like cos square of theta minus sinh square of theta is actually equal to 1. So this is kind of similar to the cosine theta square plus sine theta square equals to 1. For the cos and sinh, you actually have a modified identity. And together with this fact, you can actually prove this easily. These quasi-particles also are usually called the Bogoliubov bosons. Right, so we're introducing some new ones here. So I don't think I have time to finish this, but I want to say something sort of more in the long run. So why we're interested in this type of transformation? For this problem, of course, we're dealing with a weakly interacting BEC. We want to find the energy spectrum, and that's why we have to introduce these B's just to make sure that we can have a simple Hamiltonian at the end. But later on, we're going to deal with spin models. For the past 3 or 4 lectures, we've been talking about non-interacting bosons and fermions. At the end of the day, we also want to talk about spins, which are kind of more interesting because it's a Hamiltonian for interacting qubits. And it turns out that one of the most important techniques for dealing with spin systems or qubit systems are through the mapping to either bosons or fermions. Because you can't directly treat the spin systems analytically unless you do it numerically on your computer, which we all know is going to have exponential scaling. Unless you have a quantum computer. So if you want to deal with things analytically, try to find some behavior of the system in the larger limit, then your best bet is to actually map the spins to bosons or fermions. And there are 2 separate transformations to do that, and we'll talk about both of them later on. And if you're trying to map it into even to fermions, at the end of the day, you will get these pairing terms, and the Bogoliubov transformation is still the tool we have to use to get the actual energy spectrum. So this is not just a tool for this. This is a very important tool we're going to use later on. So I don't have time to talk about the actual transformation. I'm going to end the class here, and I'll see you next Monday. We'll continue this most mathy part. Hopefully you can survive. Yeah. All right, see you.
For these two cases, having trouble differentiating why one's like I understand that this one you're annihilating two particles equal and opposite momentum, like functions and momentum is the same, but these two look the same.
Yeah, I think it's like a symmetry thing essentially. So it's like, are you saying that it's a particle that is being created with momentum? I guess like that is